Welcome to this explainer. Today, we're embarking on what I like to think of as a sort of mathematical detective story. You see, when engineers sit down to design a system, whether that's just a simple motor or a massively complex spacecraft, they face one really critical, overarching mystery. Basically, if we turn this thing on, is it going to safely settle into a groove, or is it going to violently spiral totally out of control? Our journey today is all about the detective's process of decoding that stability. So let's dive right in and crack this case together.
Here's our roadmap for today's explainer. First, what is system stability? Second, mapping poles on the S-plane. Third, the Routh-Hurwitz criterion. Fourth, building the Routh matrix. Fifth, handling the zero traps. And finally, number 6, real-world applications.
Section 1. What is system stability?
Before we can start decoding anything, we kind of need to know what we're looking for, right? Well, in the world of control systems, stability is absolutely crucial. It's literally the single most important characteristic. If your system isn't stable, honestly, nothing else you've designed even matters. We use this core principle that says a system is stable if its response to an amplitude-bounded input results in an amplitude-bounded output. Essentially, bounded input equals bounded output. Think of it like a basic rule of cause and effect. If you give a system a limited, controlled little push, that's your input, its response should either die down, stay exactly the same, or at the very least, not blow up entirely. If the output stays within limits, we call it stable. If it grows out of bounds, yeah, we have a serious problem.
Imagine looking at the behavior of a stable system over time. What you'll notice is that the initial transient wave might spike at first, sure, but then it decays. It safely tapers off until the whole system settles into a nice, smooth, steady line. But if you contrast that with an unstable system, the story is completely different. Those waves, they don't settle down at all. They just grow larger and larger and larger. And if we're talking about a physical machine, those amplifying oscillations mean intense shaking, extreme overheating, and ultimately a catastrophic failure.
Section 2. Mapping poles, the S-plane.
So how do we spot this danger before the machine actually breaks? We use something called the S-plane. It's essentially a visual map of a system's poles. Now, poles are just the mathematical roots that dictate how the system is going to behave. And what's really fascinating here is the strict dividing line right down the middle. The left half of this plane, that is our safe zone. If all of your poles land over there, their transients will tend towards 0, meaning the system is perfectly stable. But the right half, that's the danger zone. I mean it, even just one single pole landing on the right side means the system's transients are going to grow over time. So the absolute golden rule here is that for a closed-loop system to be stable, every single corresponding pole must have a negative real part. They literally have to be on the left.
Section 3. The Routh-Hurwitz criterion.
Now you might be thinking, do I really have to solve massive polynomial equations by hand just to find where these poles are? Thankfully, no. Enter our ultimate decoder ring, the Routh-Hurwitz criterion. This was actually published independently by 2 different mathematicians, A. Hurwitz and E.J. Routh. Before we even dive into any heavy math, this criterion gives us a super quick visual check, a necessary condition for stability. You just look at the characteristic polynomial of your system. If any coefficient is completely missing, meaning it's 0, or if any coefficient has a different sign than the rest of them, you can stop right there. The system is automatically unstable. It's a massive red flag that saves us a ton of unnecessary calculations.
Section 4. Building the Routh matrix.
But hey, what if your polynomial actually passes that first test? What if all the signs are exactly the same? Well, that's when we have to roll up our sleeves and dig into the procedural part of our analysis. Okay, I know the general formulation for this matrix looks like a totally intimidating wall of algebra. It looks intense, but please don't let it scare you. While it seems highly complex in this abstract form, I promise you once you actually apply it to a real-world example, it is a surprisingly straightforward, highly mechanical process. Let's break it down into steps.
Setting up the matrix basically happens in 3 distinct steps. First, you take your polynomial and list the powers of s straight down the left side, starting from the highest power all the way down to 0. Easy enough. Step 2, you populate the first 2 rows by zigzagging your way through the polynomial's coefficients. So the first row gets the first, third, and fifth coefficients, while the second row gets the second, fourth, and sixth. Finally, for step 3, you calculate all the subsequent rows by doing a specific cross multiplication of the rows directly above them. Essentially, you're just finding a negative determinant and then dividing it by the first element of the row right above it.
And here is the absolute most brilliant part of the Routh-Hurwitz method.
Once you've completely filled out the entire matrix all the way down to the bottom row, you get to ignore almost all the math you just did. Seriously, you look only at the first column. The rule is incredibly simple. For the system to be stable, every single number in that first column must have the exact same sign. If they're all positive, you are safe. But if there's even one sign change, that is the fingerprint of instability. Actually, the specific number of sign changes exactly matches the number of unstable poles lurking over there in the right half plane. Pretty amazing, right?
Section 5. Handling the zero traps. Of course, no good detective story is complete without a plot twist. Sometimes, right in the middle of calculating your matrix, you'll hit a zero, and that zero threatens to derail our whole investigation. There are two specific edge cases, let's call them traps, that you might run into. Trap 1 happens when only the very first element in a row calculates to 0. This is a big problem because remember our formula? We have to divide by that first element to get the next row, and a division by 0 completely breaks the math. Trap 2 is even weirder. That happens when every single element in an entire row calculates out to 0. Let's look at exactly how we bypass each of these.
Okay, if you hit trap 1, meaning there's a 0 only in that first column, we use a really clever little mathematical workaround. We simply cross out the 0 and substitute it with a tiny, microscopic, theoretical value that we call epsilon. Then we just keep on calculating the rest of the matrix using epsilon in our algebra. Once the matrix is completely done, we evaluate the signs in that first column by imagining what happens as epsilon shrinks infinitely close to 0, either from the positive or the negative side. It's a fantastic trick that lets us bridge the gap without breaking any rules of division.
But what about trap 2? What if the entire row is completely zeroed out? Well, this actually gives us a really crucial clue. It tells us our polynomial has symmetrical singularities around the origin. To solve this one, we actually retrace our steps. We go up to the row immediately above the 0 row, and we use those specific numbers to form what is called an auxiliary polynomial. Let's just call it p of s. Then we take the mathematical derivative of that polynomial. And the really beautiful part? The coefficients of that derivative give us the exact numbers we need to replace our row of zeros so we can finish the matrix. Case closed.
Section 6. Real-world applications. All right, so we've done all this heavy detective work. We've mapped the poles, we've built the matrix, and we outsmarted the zero traps. But why does any of this actually matter in the physical world? Well, the tangible stakes here are incredibly high. Take a maglev train, for instance. These trains float on a magnetic cushion at incredibly high speeds. The control system keeping it levitated has to be flawlessly stable. If even one right-half pole sneaks in there, the train starts oscillating wildly and could violently crash into the track. Or think about robotic systems, like a soft-arm robot designed to help feed individuals with motor disabilities. In that scenario, a robot is interacting intimately with a human face. The position control must be absolutely provably stable, or a sudden jerky movement with a spoon could cause serious injury. This is exactly why engineers calculate the Routh matrix, to guarantee our safety.
Which leaves us with a really fascinating final thought. We've seen that strict stability keeps transients bound, and ultimately it keeps us safe. But safety often requires restraint. If we force our poles deep into the safe zone, how might those strict mathematical constraints limit how fast or agile a system can be? Just think about a fighter jet versus a giant commercial airliner. The jet actually trades a bit of inherent stability for extreme maneuverability. It is a profound engineering trade-off between safety and raw performance. Definitely something to keep in mind the next time you see a high-tech system in motion. Thanks so much for joining me in this explainer.